page 2 of the notes for vector functions and space curves. And so the first thing that we're going to talk about on this page is, it's defining if our function is continuous or not, and if it's continuous at a value a. And so the way that we tell, just like in calculus 1 and 2, the limit as t approaches a of our vector function has to equal the value of a at that function. R is continuous at a if and only if the component functions f, g, and h are also continuous at that value. So, any continuous vector function R defines a space curve C that is traced out by the tip of the moving vector. So, what our vector value function is giving us is giving us a curve in space. So, don't necessarily think of this as a line over here, the picture on our right. All right, that's going to be a curve through space. It could be coming towards us, away from us. But it's going to go in a certain direction, and I'll tell you how you can, always figure out that direction. Again, since we're using a function of t, it's a function of time. So usually we're going to start off with t is equal to 0, and then move to increasing values. But our vector function, all it is it's going from the origin. We're having vectors that are coming off the origin, and then they're creating this curve that we have. So that's what the vector function is doing. It's just shooting out a bunch of vectors that is creating this curve through space. So this is our vector function, and it's creating this curve, just for our example to the right. So what we want to do is I'm going to give you some vector functions, and I just want you to describe the curve that it's creating. In a second, I'm going to go ahead and give you some added notes of how to actually sketch these that are not included in these notes. And so if you print this off, just use the last page to write out the sketches, or the back of the last page. So for example 3, describe the curve, and we have our vector function with components 1 minus t, 3 plus 2t, and negative 5t. So the first thing that you always want to do, even when you're sketching, and I'm going to give you these rules in a second, is you want to ID what your x component is, your y component, and your z component. So we have x is equal to 1 minus t, y is equal to 3 plus 2t, and z is equal to negative 5t. Now, normally what you want to do after this is you want to either use 2 components to sketch, as some type of surface, since we have 3 components. But one thing I want you to notice is that, this should look familiar. All right, and the reason why this looks familiar, these are just parametric equations of a line. Alright, so because these are parametric equations of a line, we're going to describe our curve. Well, in this case, our curve is just going to be a line. And the reason why we know this is because we've identified this as being the parametric equation of a line. They go back to, our previous notes. This is the equation of a line. And so I'm going to say a line passing through. The point. All right, so a line passing through the point, and so we got to figure out, okay, what was our r sub 0? And in this case, our r sub 0 is going to be the constants in all of our parametric equations, not the values with our variables. And so it's going to be 1, 3, and 0. Again, that's the constant for each parametric equation. All right, I'll just identify those real fast. So it was 1, 3, and then 0. There's no value there. So that's the point that it's passing through, and it's parallel to a vector. and the vector that's parallel to is going to be now all the coefficients of our variable t. -1, 2, and -5. And that's it. We described with the curve. In this case, the curve was going to be a straight line. And the reason why we knew that is because after we wrote the parametric forms, we realized, oh, this is just a parametric equation of a line. And because we know it's a parametric equation of a line, so let me make sure I denote that equation. I can go ahead and say that it's a line. All right. And again, we can do that for this one because, we've already dealt with, parametric equations that look like this. So what happens if we are dealing with ones that, we don't already know what they look like? So let's look at B. And we have the vector function cosine t, sine t, plus t. Or cosine ti plus sine tj plus tk, so standard basis form. And the first thing that we're going to do is we're going to, again, write out all of our components. X equals cosine t, y equals sine of t, and we have z is equal to t. So one thing that's going to be very important for this section is that if you're ever given, cosine and sine together as parametric equations, for one component, then what you want to do is you want to go ahead and put this into x squared plus y squared form. In this case, because we know that cosine squared, one of our Pythagorean identities, plus sine squared of t is equal to 1. All right, and the reason why we're doing that is because what we want to do is we want to figure out, okay, if I don't know what this looks like, I want to use two of these functions to create a surface that I know what it looks like. And so we know cosine squared t plus sine squared t equals 1. Well, that's going to be, a circle. And so because x squared, so since x squared plus y squared equals cosine squared t plus sine squared t equals 1, we know that the curve must, let me write that better, the curve must lie on a circular cylinder x squared plus y squared equals 1. All right. Now, the reason we say circular cylinder is because this is in 3 dimensions. All right. What's going to happen with, the x squared plus y squared equals 1 is we're going to have, and I'll go ahead and draw this, if I asked you to draw this one's not going to be too complicated to draw. But say, okay, here's our x, y, and z plane, and I'm going to go, 1 for each of these. So the first thing is that x squared plus y squared equals 1 is going to give us the circle on the x and y axis. So we're going to have, let me change, I don't want that color. Let's go to blue. We're going to have this circle. But because this is in 3 dimensions, we can't forget about that z component. And so what it's creating is it's creating a circular cylinder because we're in 3 dimensions. And so let's see if I can do this well. All right, so it's creating that circular cylinder. And now that I have a surface, what's going to happen is my curve is going to go along that surface. All right. And so what's going to help me with that is going to be my z component. All right. Since z equals t, the curve spirals, that's not how you spell spirals, upward around the cylinder as T increases. Alright, so it's going to start, so like again, T is equal to 0, so we'll start there. If T is equal to 0, our point is going to be, you're just going to plug T is equal to 0 into all of the parametric equations. You're just going to plug it in there. And so when we do that, cosine of 0 is 1, sine of 0 is 0, 0. So it means that we're starting at this point, and then we need to tell, okay, what direction, and also, you know, what, are we increasing, going up, or are we going down? So the next value I have to take is T is equal to pi over 2. And so that gives me 0. That gives me sine of pi over 2 is 1, and then z is pi over 2. So that tells me that, you know, if we're going from 0 to pi over 2, we're increasing, and so it means that my point's going to be going up. And so if I keep going, it's going to go around, and then, and again, this is not going to be perfect. And we're just increasing as time goes on. So that's what it actually looks like if I asked you to graph it. And so the curve spirals, you know what I'll say here, just to add this there, the curve spirals, you know, let me erase this right here, just so that I can add, to be more specific, the curve spirals in a counter clockwise direction upward around the cylinder as T increases. So that's the best way to put it. All right, and that's it for B. Now, for example 4, all right, what's going to be best is, you know, I'm going to give you some rules on how to sketch. So at the bottom of the notes, add it in. Okay, I'll just do it right down here below, because you'll have plenty of time, or plenty of room to do that last problem. That last problem does not take too long. I'm going to give you some rules on how to sketch. So sketching. So when you're sketching, you know, your vector function, your curve, all right, the first thing you want to do is you want to ID the x, y, and z components. So that's the first thing. Find your parametric equations. After you find the parametric equations, you're going to use one or more components to get a curve or surface. All right, so basically what that means is you're going to get rid of T. So you're going to write your parametric, what you're going to do is you're going to solve kind of for T for one of your parametric equations and substitute that in for another to either get a curve or a surface. All right, so for 2 components, you're going to sketch on a plane. And for 3 components, it's going to be the curve is on a surface, kind of like what we did last one. All right, so if we have 3 components, all right, our curve is going to be on a surface. So we're going to take two components to find a surface, and that third component is going to help us draw that curve on whatever surface that we're dealing with. And for two components, we're just going to be able to sketch that on a plane. All right, so the third one. Use values of t to find points and orientation. All right, and that's the rules that we're going to use for sketching a curve. So we're going to do two together, one more on this page, and then we'll do the next one in the next video. So let's go ahead and talk about our vector. So the first thing we want to do is write this in component form. So x is equal to t squared, y is equal to t, and z is equal to 2. All right. Now, we wrote this, so we've worked on the first step. So now what we want to do is we want to write this in terms of, okay, is there a way that I can, solve for t to, get a curve or to get a surface that I can work with? And there is. X equals t squared and y equals t. Let's go ahead and say, well, x then has to equal y squared, because y is equal to t. And now that I know that x is equal to y squared, then it helps me figure out, what type of shape that have. So x equals y squared is going to be a parabola, and it's going to be a parabola on the xy plane. So I'm going to go ahead and draw the xy plane, and I'm going to go ahead and create the parabola real fast. And now I'm going to show how this is going to give us a surface. Because this is in 3 dimensions, all right, this is going to create a surface. And the surface that this is creating is going to be a parabola that's facing, to the positive x direction. And so our parabola is going to look something like this. All right. And, if we wanted to tell, okay, well, which direction is this going? We're shooting off in both directions for our parabola, but this is creating a cylinder, all right, because this is 3 dimensions. And so, again, it doesn't stop here. I'm going to draw a line right there. It doesn't stop there, but that just is, I'm going to extend those lines too. It doesn't stop there. I'm just going ahead, I'm drawing it so that you can see, okay, what this looks like. And so, what I'll do is I'll draw a top to this as well. Again, this is not perfect. And so here we have a cylinder in 3 dimensions. And what we're going to do is now our z component is going to help us draw what the curve actually is. And so if we know what z is, in this case, z is equal to 2, we know that because z is equal to 2, that's what our curve is. So z is equal to 2. And so then our curve is only going to be at 2 on the z-axis. And it's creating this shape. So what's in red is the solution. All right? And we basically graphed it. Again, you did not have to draw the cylinder. You could have simply went up 2 and could have been done this way as well. All right, you could have easily have done that, but I just wanted to show you how, we're going to, combine two components to create a surface, and then whatever third component we didn't use, that's going to help us actually draw what the curve is going to look like. All right, and so just showing you that the two components are going to create a surface. All right, and that's it. That's the answer. And again, if we wanted to do direction, again, I have it going both ways, but the direction as t is increasing, it would go in that direction.